welcome you all. Today's topic is chirality and symmetry elements, and we'll also discuss about the projection formula. So coming to the subtopics of the main topics, we are going to discuss with element of symmetry, projection formula, Newman and Sawhorse projection formula. So in this will see how the symmetry plays a very important role to having some certain kind of chemical reactions. So before to know what is the symmetry is, so the symmetry is, when a shape looks like identical to its original shape after being flipped or turned. So here you can see here in like this plant, if you can say having the symmetrical, once you pass the plane from here, so it will be dissecting this in a same plane. So here if you see here, so the half of the lobe of this is different from this one. So this is the asymmetric. So here you can see mostly the symmetric are having more stability in terms of we are talking in any of the molecules. So most objects found in nature have symmetry. So symmetry is having associated with the beauty. Many flowers you can say if you bisect it, so it will be bisecting in equal halves like diamond, butterfly, snails, leaves, etc. And they are having the highly symmetricals, and therefore this symmetry is having also very important role in case of once you are talking in a certain kind of chemical reaction. So here we can go with the symmetry. So here if you see, it is like a geometrical entity like such as a line, plane or point about which one can perform an operation of rotation, reflection or inversion. A symmetry operation is movement of a molecule, objects about and symmetry element such that resulting configuration is indistinguishable from the original one. So it can be watched by taking the example of like in case of water molecule. Once you rotate about an axis through 160-degree like this, is this from the center of axis. So by the C2 axis, C2 means 180-degree of the total 360-degree of this total circle. So you will see here the molecules will looks like HB will be like this side and HA will be opposite of that. So this is a 180-degree rotation. So here and this is, you can see, is having the same mirror image also ones to each other. So here like the symmetry rotation molecules is having 180-degree rotation. So first and second are equivalent, second and third are equivalent, and one and third are identical. Identicals means one is having the same if we designate it like HA and HB. So you will see in the same position of these molecules of having the atoms are the same place. So if you see in a summarized form or starting, we are going with the different kind of symmetry elements and their operation. So here you can see in case of identity in terms of once if you will look at in a molecules. So if the molecule is having the identity, so it means there is doing nothing to do with the any kind of operation. It will looks like the same. And proper rotation axis or axis of symmetry, if it is having certain angle of rotations with like 90-degree, it could be 60-degree, it could be like 180-degree. So accordingly the number of n is the total rotation, like suppose C2, so it means there is 180-degree. If it is C4, then it means there is a 90-degree rotation of the particular atom associated with that molecules. So here similarly mirror plane of symmetry, reflection about the plane in that case. If it is the symmetry element in inversion center or center of symmetry, so inversion is reflection about a point. Improper rotation axis of or rotation reflection axis, so rotation about an axis through some angle followed by a reflection in a plane perpendicular to the rotation axis. So these all we will go in details and we'll take some example each of these symmetry elements. So before going to in details, so now coming to element of symmetry. So as there are, enantiomerism depends on whether a molecule is not superimposable on its mirror image. So if it is superimposable, the molecule is optically inactive, otherwise it is optically active. So for to check or for the convenient method of inspecting superimposability is to determine whether the molecule has any of the following for element of symmetry. So here you can see there are different element of symmetry like identity, because this is the same, we have not do anything with that, so it is generally not considered most of the time. But there are four important element operations. Here you can say proper rotation axis or axis of symmetry, plane of symmetry or mirror plane, inversion center or center of symmetry, alternating axis of symmetry. So these all we will going to discuss one by one in a next one. We'll go this. So here identity, this is an operation which brings molecule back to its original orientation. It means there is nothing to do with that the molecule, because it will take the safe and even more accurately the size, the position of the particular atoms will be at on the same place. So this operation does nothing, it simplify all the symmetry elements. It is the only element operation possessed by all molecules. Like for example, here it is the example of a molecule which is having like center carbon, hydrogen, bromine, fluorine, and four different atoms. So here you can see this example. Now the another important operation which is proper rotation of axis of symmetry, which is also called CN symmetry operation. So here an imaginary line passing through the molecule in such a way that when the molecule is rotated about its by a certain angle, like here you can see like 180-degree rotation is there. But similarly it could be like suppose you are rotating with respect to 90-degree or some other angle. So then similarly here C2 symmetry, because C2 symmetry means here 360 by 2 if you are making, so it will be rotating by the 180-degree. So here you can say how does the molecules is changing from their positions with respect to, you can see this molecule is coming this side, this will be the 180-degree for this, and this molecules will be going to this side. So here by this type of operation, if it is there, then that is will be called as proper rotation or axis of symmetry. Now you can take some more example, like here you can take the water molecules also. Here also 2 pi, this is 360 degrees celsius degree rotation. So here by n 180-degree if you are making, so C2 symmetry will be there. So there is some more example like BF3. In case of BF3 you can see here is C3 axis of symmetry, because here the rotation with respect to this central atom will be like 120-degree. And here in case of nickel tetra cyanide, so here you can say C4 symmetry operation is there. Similarly in case of benzene you will find C6 symmetry operation. So it means that is by the angle, if you see like 60-degree rotation of the actual position of the atoms. So now coming to the another symmetry operation, which is plane of symmetry or mirror plane. So a plane of symmetry is defined as an imaginary plane which divides a molecule in such a way that one half is mirror image of the other half. So a molecule with at least a plane of symmetry can be superimposed on its mirror image and is achiral. So this is very important. If you see the plane is going to be passed over the molecule that does not have a plane of symmetry is usually is chiral. So here now we have to see how much mirror plane is there. So if you can classify them, so it could be classified on the basis of here like vertical plane. This is the principal axis of symmetry lies in this plane, and in case of horizontal plane the principal axis of symmetry is perpendicular to the plane. And in case of dihedral plane, so the plane passing through the principal axis but passing in between the subsidiary axis is the dihedral plane. So now coming to this, here you can see a plane of symmetry may pass through atoms between atoms or both. So here you can see here is a plane is going to be passed. So by this way the molecule is like tartaric acid. So once you superimpose this part of this, so it will be like equal half of the whole molecules. So here plane is going to be passed horizontally. So now here if you see, like in case of water molecules, here vertical plane can be passed over here. So in this molecule, horizontal plane can be passed in a mirror plane like this way. So this is having sigma H and sigma B in case of water molecule. So there are a number of examples you will find where the plane of symmetry or mirror plane symmetry will be there. So another symmetry operation which is like inversion center or center of symmetry. So here the inversion center you can say in any point where you can connect the molecule from one remote position of the atoms to with respect to the another remote position. So here it could be a molecules or atoms or group of atoms. So here you can see the one plane can be passed which is passing from the center of the whole of this molecule. So here if the plane is going to be passed, then obviously this will be the trans chiral molecules of this molecule. But once you see in a cis molecule of the same, so this is chiral. So it means there is a chirality is there, chiral center is there. So similarly you can understood it by with the help of ball and stick model. Here if you can say here the center, if you see this atoms which is attached with the this molecule can be passed over here. So this will pass within a certain center. So there will be a center of symmetry. It will, you can see here by the different color it is being represented, white and white. So it will be passed. So this will be, this kind of molecule will be achiral. So by the with the help of symmetry operation you can easily find out which molecule is chiral and achiral. Another important operation which is also being important during the course of various chemical reaction, which plays a very important role to whether the reaction will be proceed forward or not, or by which rate it will be accomplished, can be also look at with the help of another type of symmetry operation. So here like alternating or improper axis of symmetry or rotation reflection axis. So this is, if you see by this is an example has been given for like 2, 3, 4 tetramethyl cyclobutane has S4 symmetry. So S4 here, what is the meaning? It is not actually the C4, but this is what is the difference here is like, suppose here if you see the molecules were like this and it can be written like this. So the molecules which is having this molecule is, if suppose you just take the mirror image of this molecule and this mirror image is being, if suppose, so the symmetry element is denoted as S2 here in case of if the rotation is 180 degree. So there are number of examples. This is one of them to check the operations here by putting this, like if you're putting the image, mirror image. So you can see here this will looks like just the mirror image of each other, and this molecule are apart from the this carbon-carbon double bond. So in that case you can see these are the mirror image of each other. If there is a double bonded molecule is there having different groups. And now coming to the various the projections formula of chiral molecule. So the chiral molecule, as you all know, having the center of carbon which is more relevant to the different atoms which is associated with that particular molecules. So here now one by one, if the the configuration of a chiral molecule is three-dimensional and it is not very easy to depict it on a paper having only 2 dimensions. So to overcome this problem, the following 4 2-dimensional structure known as projections have been evolved. So among them, this one is like first one, Newman projection, Sawhorse, Fisher projection, and flying wedge formula. So among these, one by one, we will move by taking some example of the certain type of projections structures, because these are very important to nomenclature as well. Once you will give the nomenclature to the particular organic molecules. So coming to this first one, as you say, Newman. So Newman projection, in this we have to look at the molecule down the length of a particular carbon-carbon bond. The carbon atom away from the viewed is called rear carbon. So here it is just a representation, and how to look the molecule is very important. So it is then represented by a circle. The carbon atom facing the viewer is called front carbon atom and is represented as the center of the above circle, which is shown by the dot. So here one carbon will be represented by the dot, and another carbon, which will be the front carbon, is represents center of the above circle, which is shown by dot. So the remaining bond on each carbon are shown by small straight line at angle of 120 degree as follows. Here the bond joined to front carbon intersect at the central dot, and bond joined to the rear carbon are shown as emanating from the circumference of the circle. So here once you will see the example, it will be more easy. So this is like this dot is, which is right now is front carbon is pointed as a dot. So here if you say this is the rear carbon, and rear carbon you can see it is like a circle, and this is like in case of if in having a straight another carbon, this carbon is attached with another carbon having the same kind of atoms attached within this manner. So the first the rear carbon, which is this one, this rear carbon will be shown as this carbon, and the front carbon, which is from your from you can view that carbon, so this will be represented as in a point. So this is, you can see here, it means this is having one carbon, another carbon. So this is the carbon is having the different atoms which is attached with this, and another rear carbon is there. So with this rear carbon you can see the Newman projections with various different forms, staggered, eclipsed forms of the same. So the Newman projection, as we discussed in above slides, is in case of like Sawhorse projection. So in Sawhorse projection, you can see here, this can be even also we can convert from Sawhorse to Newman projection. So the conversion we will discuss on later. First of all, we are going to discuss about their individual how to represent them in case of the Newman, in case of Sawhorse. So as you've seen in case of Newman projection, that is being represented in a circle, and rear carbon in a circle and front carbon as a point. So here in case of Sawhorse projection, which is can be also converted into the Newman one. So in Newman's, if we are going to convert, then at the time of conversion, we will see the different molecules how to convert in their different forms. So here, like the bond between two carbon atoms is shown by a longer diagonal line, because we are looking at this bond from a oblique angle. The bond linking other substituent to these carbon are shown projecting above or below this line. So what is the meaning of this? Means like suppose you have a carbon which is another carbon, like in general in paper you are representing the carbon like carbon. So here how you are representing it in form of Sawhorse, and in Sawhorse there is another important points which is their arrangement as per either that the molecule is totally staggered or eclipsed. So what is the difference between eclipsed and staggered means? Here if you can see this, so this is like making a Y kind of inverted Y shape. So these atoms are arranged in this way, And if you say this is a regular Y type of arrangement, so here if you want to superimpose this, so this Y will looks above of this, and these will comes to this side once you will put it into the Newman projection formula. So here this can be converted into the eclipsed form. So because why we are very concerned about staggered and eclipsed form, because you know there is different kind of force. So these are the references and source from where these slides had been prepared. So you can refer these references, online materials as well. Now summarizing the whole discussion of the lecture today's. So in overall, if you see, we had gone through different kind of symmetry elements, symmetry operations. Among them there are total 5 operations. Those operations are specifically is being important as we see the molecule, how in 3-dimensional space the molecule is being arranged in different different molecules. So the molecule, because that is very essential once you see their specific reaction with respect to a particular kind of reagent as well, because the chirality plays a very important role, and that makes the essence of either the reaction will be proceeded at what rate and what kind of conditions will be required. So the operations, like in case of symmetry operations, the molecule is going to be changed from their specific arrangement with respect to their central axis. So if it is rotating, like in case of C2, like for example in a molecule which is having C2 axis of symmetry, so it means the atoms from their original place is rotating with 180-degree angle. It means total 360 angle divided by 2. So it will show the number n is number of rotation, like 2 rotation 1 degree, it is showing if 180 or 60 degree, it means total 360 by 6, so it will come 60 degree of rotation in case of benzene molecules. Like if you are taking the example of like BF3 molecules, so in case of BF3 molecules it will be like C3, because 120-degree rotation will be required to check whether what kind of so similarly improper axis of symmetry, and improper axis of symmetry you can see by taking the molecules and their mirror image and reflection over the with the original molecule. So if it is the reflection of that, so that will be called as improper axis or alternating axis of symmetry. So after that we also discuss about the projections, because these are the representation of the molecules and these are interconverted to each other, as well as it helps us to find out their nomenclature, like RS nomenclature, if you want to designate the molecule in with their respect to rectus to the, if it will rotate the plane polarized light towards the rectus, and levorotatory rotation. So rotation with respect to the plane polarized light can be also checked in case of that. So coming to Newman projection, you had also seen staggered form of that, and staggered at eclipsed form. So because this is representation with respect to energy context also, because the molecule, if it is having more stability, whatever is the form, so it will try to exist in a more on that forms. But if the energy is less of the any of the forms, then it will be exist in a lesser way, because this plays a very important role once you are taking as a substrate during the kind of reaction. So it affects the formation of the product at the same time, because the product formation will go change because the availability of many theories which states about the formation of particular kind of product. So you also know like different theories which explain how the different forms and stability of the respective substrate plays a very important role with respect to the formation of the product. So Newman, after Newman, we also discuss about the Sawhorse. Sawhorse, in that case, it is represented in a simple, like a bond is represented in a simple line, and after that the atoms are represented. Similarly, we can also see the molecules if having a different atoms or groups in a form of their staggered and eclipsed form. So those are having role in their stability. So overall, we discuss all about the basics of this. So thank you for all of your listening essentially.